My name is Anneli. This week p-value made it to the science newsfeed. The whole story started already last August when Benjamin and some 80 co-workers published in Nature Human Behavior a paper called Redefined Statistical Significance. They claimed that the p-value that we call statistically significant should be reduced from 0.05 to 0.005. with the aim of making the scientific research better repeatable. This week, Lakens and another 100 co-workers published a response called Justifier Alpha, with the aim of defending the p-value 0.05 as statistically significant. They point out that lowering p-value would significantly increase the size of scientific studies. If p-value that we call statistically significant would be reduced, scientists would need to study far more samples to obtain the same result. This, on the other hand, would make the research much more time-consuming, of course more expensive, and would make it less likely to be repeated by other scientists. So what's the fuss about this p-value? Students don't like p-value, it's a bit complicated. Scientists are mostly interested of finding out if the result is statistically significant or not, and even science says that it's kind of fuzzy, the understanding of p-value. So I shortly try to describe what p-value is and bring out the benefits and drawbacks of lowering the p-value. So I try to explain this p-value based on an example. Let's say that we are doing some climate studies and we are interested in the average temperature for the last 10 years and between 1950 and 1960. Usually when we do science, we are looking into some differences or similarities. Unfortunately, statistics do not allow us directly testing if some parameters, for example temperature, are different from each other. We can only test directly if the parameters have equal values. Therefore, the whole concept relies on two hypotheses. The first hypothesis is that the parameter has the value that is equal for two conditions. So, in our case, the temperature for last 10 years and the average temperature for 1950 to 1960 is equal or indistinguishable. This is called the null hypothesis. There always has to be also another possibility. So this is called the alternative hypothesis, and it is that the average temperature for last 10 years and for 1950 to 1960 are not equal, the temperatures. Now comes the p-value into play. Because of the random variations in our measurements for absolutely all possible parameters, there are small differences that vary from experiment to experiment. For example, in case of temperatures, this could be the small variations in the instrumentation, sudden geological processes, and others. So there always is a variation in the temperature, which causes us also uncertainty in the average temperatures. So it never happens that the two parameters under two different conditions that we are trying to study, for example, now the two average temperatures are exactly the same. So this variation also makes it hard to decide if the temperature actually are the same or they are not the same. So in reality, it can be that the average temperatures for these two periods are equal. But based on our statistical tests that we carry out, there are two possible outcomes. It is that the temperatures are assigned as equal, or that they are not assigned as equal. So it is that we either accept the null hypothesis or the alternative hypothesis. In the first case, where we stay with the null hypothesis, the decision we make is the same as is the reality. However, we do not actually know this. The other possibility is that even though the temperatures actually are the same, that there isn't any real change in the average temperature, but there are only small variations in the temperatures that come from additional sources, we may say that, oh, the temperatures are different. This, however, is not correct in the terms of reality. So we would like to make such a conclusion only very rarely. This kind of failure in our analysis we call the false positive. And this false positive actually is the p-value. So, for example, if we say that the p-value that we call statistically significant is 0.05, then this means that we say that it is unlikely to say that the average temperatures are not equal if they actually are equal. Of course, from this perspective, it would be very good if we would keep the p-value as small as possible, because then we would assign a difference only very rarely when there is no difference. However, there is also the other pole. It may also be that in reality the temperatures are not equal to one another. And we may still make two conclusions from our statistical tests. We may conclude that the temperatures are the same, or that they are not the same. If they are actually not the same, and we also say that they are not the same, everything is fine. However, it may also be that we say that the temperatures are indistinguishable, even though there is a difference in the average temperatures. This is also a faulty result that is called false negative result. However, if the p-value is directly tested and we can always state what our p-value is, the false negative rate is unknown because we do not know how much the temperatures actually differ, and therefore we can't calculate what the false negative rate is. The only thing that we do know is that if the false positive rate goes down, the false negative rate goes up. This means that if we make the p-value that we assign as statistically significant smaller, the possibility that we assign the temperatures as equal if they actually are not equal becomes higher. So let's try now to see it in a bit different context and see how big problem this could actually be, and how does it influence our choices of p-values that we assign as statistically significant. So let's say that we are doing some drug analysis and we are looking for compounds that could be possible drugs. So in this case, we pick a big set of compounds and we try to compare them to the placebo and try to find out if the effect of this compound is different from the placebo or if it is the same. If there is no change between the compound and the placebo, and we say that there is no effect and the compound probably is not a drug. However, if the compound is more effective than the placebo, then there might be an effect and this compound could theoretically serve as a drug. So there are, again, 4 different possibilities. The first possibility is that in reality the compound does not have any effect, and our statistical test also confirms this. It is also possible that the compound has an effect, and we can also reach this conclusion with our statistical tests. But there are also possibilities that the compound does not have any effect. However, we conclude from our analysis that the compound is a potential drug. And there is also the other possibility that we conclude that the compound does not have any effect. However, it might actually be a drug. So which one now is more problematic? Either assigning a compound that is not a potential drug as a drug, or vice versa. So usually such drug studies are involve very many different levels, and the first level of such studies often is by doing computational chemistry. So by observing with the computer calculations if the compound has the properties that are needed for a drug. However, such studies are prone to errors, pretty big errors, and it is possible that we lose quite a bit of compounds in the coming steps, which involve chemical tests, biological tests, safety tests, and so forth. So it is possible that we lose most of the compounds that we choose in this step in the coming steps. So in this first step, we actually would not like to lose any compounds that are real drugs. So we would like that if the compound in reality has an effect, it would not fall out from our studies in the coming steps. So in this case, we would like to keep the false negative rate as low as possible. And as false negative rate and the false positive rate are inversely connected to each other, in these cases, in the first picking of the compounds, we would actually like to make the false positive rate a bit higher to keep the false negative rate pretty low. So in this first step, we would like probably to have a p-value that we assign as statistically significant about 0.05 or even 0.1. However, now when we go on to start doing some chemical tests, and maybe the next step is already some animal tests or some biological tests, which are very time consuming, very costly, and also may be harmful for the animals, for example. In this case, we would like to choose really only the compounds which are really possible drugs. So in this case, we would not like to take to the biological tests, for example, the compounds that actually do not have any effect, because it would be bad for our costs of the drug, also from the time wise, it would not be very good. Therefore, in this case, we would like only to take compounds that actually do have an effect and that we also assign as having an effect. In this case, we therefore would like to make the false positive rate as low as possible. For example, maybe even 0.01 or 0.005. So now there is only one small thing to clear. There is only one possibility to make both the false positive and the false negative rate smaller at the same time. And this would be to increase the number of data points. So in case of the temperature example, it means that we should gather very, very many data points, maybe thousands, hundreds of thousands, to actually make the conclusion. These are the main reasons why there can and should never be a fixed p-value that we call statistically significant, and why it should be adjusted each time according to the aims of the research. Even better would be to report the original data together with the p-values obtained and with the conclusions of the authors, so that the reader would be able to draw the conclusions that are relevant to him or her. See you next time!